So thanks also to the organizers for this conference, which was wonderful so far, and for the invitation. So yeah, so I'm going to talk about something we've been trying to do for some years, and we were always like thinking we were close, and it never worked. And recently we finally managed to do it. So it's about the diameter of high genus random triangulations. And the ingredient that finally made it work was isoperimetric inequalities. And so I will start with something which are not so new, because Elba asked me to review a little bit also part of the context. But the new results will all be joint work with two brilliant young people who are here, Thomas Budzinski and Baptiste Louf, respectively from Lyon and Bordeaux. Right, so does this work? Yes. Okay, so let me start with maps. So I will talk about combinatorial maps. So for me, a map of genus G will be something like this. So you have a graph, and it is drawn without edge crossings on the oriented compact genus G surface. So no boundary, genus G, and I ask that the faces are disks or polygons, if you wish, and I consider these things up to homeomorphisms. So here my graph is allowed to have little loops or multiple edges. It would be more precisely a multi-graph. So equivalently, because I caution by homeomorphisms, I can also think of these objects as some purely combinatorial data. Giving you a map is the same as giving you a collection of polygons. So here, for example, one quadrangle and two triangles, and a collection of identifications between edges. So this combinatorial data is in fact exactly the same as the topological definition. And I just ask that my object is connected. And then when I talk about a map of genus G, I require that the genus of the final surface that I get by gluing is precisely G. So I'm not really a topologist nor a geometer. I'm one of these counting person who just likes close formulas and these sort of things. So these people, I mean, at least in France, they are called combinatorialists, and we like maps because maps are fun to count. So in fact, there is a whole part of the combinatorics community that just counts maps. And you can spend your whole life counting maps, and that's more or less what I'm doing. So that's really, so this is where I come from, and this is the basic motivation for me, is to have fun with the counting of these objects. Maybe one thing that I have to say at some point, my maps are all rooted. This is a technical point, but when I say a map, I always assume that somewhere an edge is oriented and distinguished. This is called the root, and this is just to avoid considerations of symmetries when I take these objects. I mean, rooting an edge is sufficient to kill all automorphisms, and so I will do that. Okay, so maps are fun to count, so some people do that, but here I will be interested about something closely related, which is random maps. So what's a random map for me? So I'm going to take a map uniformly at random among the finite set of maps having genus G and size n. And this will be a random map for me. And sometimes, in fact all the time in this talk, I will have some constraints on the phase degrees, or weights on the phase degrees. So the two basic things that I will be interested in are triangulations. So T and G will be the set of triangulations of genus G and size n, which means 2n faces here. So you just take your polygons to be triangles. And bold T and G will be a uniformly random element in this set. So this T and G, this is a random variable, it's just a triangulation that you choose at random among the ones having size n and genus G. And I write it here. At some point I will need this number, which is the cardinality of this set. So this tau and G, I will recall it, it's the number of triangulations of genus G and size n. And another model which appears a lot in the literature are bipartite triangulations. So this time you do it's the same thing, but you take quadrangles, and you also require the thing to be bipartite. So you mean that each triangle has two colors of vertices, and the gluings preserve the colors. So basically, depending on the questions you ask, sometimes it's easier the easiest model is triangulations, and sometimes the easiest model is bipartite triangulations. It is more or less always the case that if one result holds in one case, it also holds in the other one in some analogous way. But depending on the question you ask, sometimes one is much more complicated than the others. And in this talk, I will always state the simplest one. My main goal is to arrive at some model of triangulation, but in the review part, I will mention bipartite triangulation, but just assume that I mean, it's more or less the same. I mean, the same phenomenon happen. Okay, so I want to look at these things, and I want to do probability, so I want to take one at random and say something about it, right? What do they look like? And typically n will go to infinity. So I want to take a very, very large one and say something interesting about it. So of course, it depends what you're looking at. You can ask different questions. But very roughly, you can separate the question between local questions and global questions. So you can look at what happens locally around one vertex, or you can look what happens globally on your graph, and these are kind of different questions, and it's a kind of rough way to separate the topic into two pieces. Okay, so what do I mean by that? Let me give an example. So for example, if you look at, if you're interested in the local behavior or typical theorem, or maybe one of the first theorems, at least in mathematics, about this is this famous result by Omer Angel, who's here, and Oded Schramm in the 2000s. So if you take, so this is a planar case, genus is 0. You take a random triangulation of genus 0 and size n uniformly at random, and you let n go to infinity. So it's something like this, but n becomes very, very big. Then it converges when n tends to infinity to something called the uniform infinite planar triangulation. What is this? This is a certain random triangulation of the full plane. So it's now an infinite object. It's a locally finite but infinite triangulation of the plane. And for the local limit topology, I will say what it means. And I will also say that one of the reasons you can do this is because you can count. So what do I mean by this? So what is this convergence here? What does it mean that a finite triangulation converges to an infinite one? So what you are able to observe are finite neighborhoods of the root. So what you're allowed to do for this topology is to fix a test map. So you choose your favorite map, a finite map, maybe with m triangles and perimeter p, and you will look at the probability that your random triangulation looks like this. So in the neighborhood of the root, you have exactly a copy of this test map that you have chosen. And this convergence means that this probability converges to the same probability in this infinite object for any map that you choose. So these are your observations. So this is what the local limit means. You're allowed to observe finite neighborhoods of the root, and whichever neighborhood you observe, the probability to see this converges to something. And it's kind of natural to see that, I mean, what is this probability? If you want to have a triangulation like this, if you remove your test map, you have a hole of perimeter P, right? So this B should be a P, or this P should be a B for boundary. And so if you know the total number of triangulations of genus 0, and if you know the number of triangulations with a boundary of size B and slightly less triangles, because you have removed m triangles, then this ratio is exactly your probability. And if you have explicit formulas for this, maybe this converges to something explicit, and you can show that this probability converge. Okay? And as I said, I mean, in the combinatorics literature, people like to count maps, and in fact, the first one to do that was Tutt. So Bill Tutt influenced many areas of discrete math in the second half of the 20th century, but in particular enumeration a lot, and he was the first to be interested in planar maps. And among other things, he obtained explicit formulas for these numbers. So you just take this ratio, you know that you prove that this converges. And then you have a lot of work to do to say that these numbers that you have here, they are indeed, they correspond to probabilities of the neighborhood of your root in certain uniform infinite planar triangulation that they construct, and then you can say many interesting things about it. But so this statement is typically what you look for when you look at local behavior. And you have analogs of this for example, for quadrangulations, you would have the UIPQ, or you have other constraints. You can get different objects. It is more or less technical to prove depending on what exactly you want. So that's for the local behavior. I will not talk about the local behavior of in genus 1 or genus 2 or genus 3 because it is essentially the same. So if you just look at finite neighborhoods of the root, you are not able to detect the fact that your map has genus 0 or genus 1 when n goes to infinity. So no one has ever done that as far as I know, but everyone believes that it will be, it leads to nothing different. Right? Okay, so then what about the global behavior? I wrote planar case, but in fact I should have written fixed genus because then I changed my slides, but I forgot to change the title. So so now you fix your genus. And I'm going to give a typical statement about global properties. So, and this time I give it for quadrangulations. So it's a very famous result by Chassin and Schaeffer by about the same time. That if you take a map of genus 0 and size n, and you let the diameter grow, you let n go to infinity, so you have this random object, and you would like to see how big it is. So by diameter, I mean the diameter in terms of the graph that you see. well, then this graph essentially has diameters that scales at n to the 1/4. It's non-trivial. I did not tell you yet why it is true. And this is true for the diameter. This is also true of the distance between 2 points. So these things are, that's random variables, but you have to scale them by n to the 1/4 in order for them to be tight. And you can also do the same in any fixed genus. So this is, this is a very impressive result, and I will tell you why it is difficult to obtain. Of course, this was just the beginning of a much deeper story. So now people, 20 years later, have done much more, and people can show the convergence of the whole metric space. So here are like the modern type of global statement that you get. So what people do, they take this random triangulation of size n and genus 0. So it's a graph, and so it's a graph. So you have a graph distance on it. You can see it as a metric space, and you just renormalize this metric space by what you have to. So n to the 1/4. And people can show that if you put a certain topology on metric spaces, which turns out to be the Gromov-Hausdorff topology, then this converges to some limiting object that looks a little bit like this. So you have one such object for any genus, so it's called the Brownian map in genus 0, or the genus G Brownian map or Brownian surface in higher genuses. So this is also a very famous statement by Le Gall and Mermont that was generalized to arbitrary genera for genus G. So what it means, if you fix your favorite genus and then you let n go to infinity and you take a map of size n, if you look at it from sufficiently far away, so far away really means n to the 1/4, you see a picture like this. So you see a certain compact, very random object, which is one of these Brownian surfaces. So this is like the best kind of global property that you could hope for. This tells you really very finely what your object is globally. And one thing which is interesting is that, this is really difficult to get. You really need also some combinatorial technology for this, but in fact you need more than counting, you need bijections. And I will not really use bijections in what I'm going to say about the new things, but just out of respect for my community, I will still show bijection. I have to do that. So maybe you've seen it several times, but it's always nice. So people call it sometimes the Scheffer bijection. The full name should be, in the case I'm going to show, the Corey-Vauquelin-Scheffer-Marcus bijection. So it's great. So on the left, so the right is the same as the left for now. Anyway. You start with a bipartite triangulation with n faces, okay, like this, on, say, a genus 1, but you can take genus G, and for some reason you mark a vertex. Okay, so this is my marked vertex, and then I'm going to label the vertices of my triangulation by their distance to the root. Okay, so this one has labeled 0, the neighbors have labeled 1, the neighbors have labeled 2, and so on. Okay, that's just what you do. And then you realize, so because your graph is bipartite and by the triangle inequality, the label has to vary by exactly 1 between 2 vertices. And now if you look at the face of your map, if you call I the minimum label in your face, you have only 2 types of face. Maybe you have I plus 1, I plus 1, or I plus 1, I plus 2, I plus 1. Okay? It's just an observation that comes from the triangle inequality. And then you have these crazy rules due to Gilles Scheffer, called the Scheffer rules. In the first case, you do that, and in the second case, you do that. Okay? It's just, how do you find this? I have no idea. And you do this in all the faces of your map. Okay? So you get some blue graph drawn on your surface. And here's the claim. These blue graphs, a priori this blue graph could be anything. It could be disconnected, it could have several components, it could have many faces or whatever. But the magic of the CVSM bijection is that this blue graph is just a one-phase graph on your surface. So if you view it as a ribbon graph, it has only one border. So if you just look at the blue graph, it's a one-phase graph, and if you look at the labels on this blue graph, well, in fact, you see that there are one Lipschitz, because by construction, the label along an edge only varies by 0 or 1. So what you get on the right, if you only look at the blue graph with the labels, it's a one-phase map with n edges equal to the one Lipschitz labeling of the vertices. And the craziness of the Scheffer bijection is that this is a bijection. So if you have the blue graph and the labels, you can go back. Okay. So that's, there are, between the first and the last paper, there are more than 20 years in these names. So that took some time to develop such a powerful technology. This is extremely powerful because on the left you have a very complicated object, a quadrangulation of genus G. You can have very long cycles. I mean, it's a very complicated object. On the left you just have something with one face, which is much simpler. And just to show you why it's useful, so let's look, for example, at genus 1. So what does it mean for a map of genus 1 to have one face? Essentially, it means that it looks like this. Essentially by Euler characteristic argument, I mean, a one-face map can have only finitely many cycles. So in genus 1, it can have only like 2 independent cycles. And so one-face map, in fact, is formed by a small kernel, like this one, for example, with 3 edges in genus 1. And then you substitute the kernel by branches of trees. And for a fixed genus, you have finitely many such kernels just by Euler characteristic arguments. And so the Marcus-Scheffer bijection, the Corey-Vauquelin-Marcus-Scheffer bijection transforms you something like a quadrangulation, which looks like a very complicated object, into one of these things. And it's a huge simplification. You can even count, I mean, what is the maximum number of branches. And so to come back to our main question, I mean, which are like global properties of the maps. So you see, I'm going to be a bit quick here, but if you take each of these branches is some sort of random tree. Okay, if you cut here only the blue branch, it's a tree. And if you take a random tree, random trees have diameter square root n, typically, when you take them at random. And then the one Lipschitz labeling that you have on your random tree is essentially a random walk on the branches of your random trees. And because your random tree has branches of order square root n, the elevation of this random walk is of order square root of square root n, which is n to the 1/4. Okay? So this bijection directly gives you access to the order, so to the typical order of these labels, and these labels are just the distances of the map by construction. Okay? And so this is precisely what you do to show the theorem that was before. Okay? So this is the reason why the diameter in random quadrangulation is of order n to the 1/4. In the plane, these would just be trees. In higher genus, these are like gluings of trees, but it is not much more complicated, and then you have this n to the 1/4. And these bijections and variants are also the starting point for all the people who do Gromov-Hausdorff limits of maps. Okay, so in the end, I mean, it's much more complicated, but you look at this from very far away, you try to understand what happens when you do the reverse bijections that I did not show you. And if you're good enough, you manage to show convergence to the Brownian map. And also, I mean, these bijections are very robust. For example, 2 days ago, Timothy has given a talk about bijection for hyperbolic surfaces with all these cups and angles and everything, which is, in the end, is one of the many generalizations of this Marcus-Scheffer bijection. Right? I don't know how to spell Hausdorff, but I don't want to learn. Okay, sorry. And also, you can also use this bijection to do some sort of approximate counting. So I want to be rough. I don't want to be too precise. That's not my main point. But essentially, if you know how to count trees, and you know how to count trees because they are just counted by Catalan numbers, you can very quickly count. I mean, you have some power of n to choose your branches. You have some Catalan numbers to put your trees. Then you have some power of 3 to put your Lipschitz random walks. Then you have some correction number because you see there's something happening around cycles, but if you're good enough, in the end, you can count asymptotically these objects just with this bijection. So this is some sort of subliminal statement that you can come back to because the thing is recorded. But my point is that in the end, with this bijection, the strongest thing you can prove at the enumerative level is something like this. So originally, the result is due to Bender and Canfield. This A is an end. If you fix your favorite genus, then you want to count quadrangulations of size n and genus G. When n goes to infinity, you have an asymptotic pattern like this. So you know exactly how it grows. You have some power of n, you have some correction exponent, which is like 5/2 of G. And then you have a certain number Tg. And this number Tg, they are computable by a very complicated recursion on the topology. So by the way, for people interested in topological recursion, this paper is essentially like the prehistoric version of the topological recursion. What they do is essentially a version of topological recursion, even if it did not exist at the time. But this paper doesn't tell you anything meaningful about these numbers and the bijection I showed you before, neither. It just tells you that for each genus you have some finite data, and this finite data altogether creates some constant, but you cannot say anything. But my point is that, in fact, some people can say something. So in fact, these numbers TG, so that the numbers that govern the asymptotic growth of maps of very large size for fixed genus, they are in fact given by a very simple recurrence formula, quadratic recurrence formula, which is here. So this goes, this comes from a connection between maps and the KP hierarchy. So for people who know, I mean, you can prove this either by algebraic combinatorics or by orthogonal polynomials and matrix integrals. And so yeah, in the literature about random matrices, this recurrence is essentially the double scaling limit for the JUE random matrices. And this is a combinatorial mystery. So when you see this, you would believe that, I don't know, there is some surgeries that you can perform on surfaces of genus J+1, so that maybe sometimes you cut it in two pieces, or sometimes you cut a handle and you get something of genus G. And this is something that we cannot do. Okay. So my point here is that people are very happy to have shown the convergence of random coagulations of fixed genus to Brownian surfaces, but there is probably much more to the story. These surfaces, they are connected together by some operations that we don't understand, but there is some relation not only for, not only at fixed genus, you have some nice object, but there is something that happens when the genus grows, and we still don't know exactly what is the nature of this phenomenon and what will be the theorem in the end or the conjecture, but there is something happening that we have to understand. Okay, so the story, even in fixed genus, is not completely finished. And by the way, I want to advertise my favorite conjecture. So fix your favorite genus G and take a very, very large random map. Okay, or maybe you directly take a Brownian surface of genus G. And you take 2 points at random, P1, P2, and you do a Voronoi tessellation. So you split your map in two, with the points which are closer to point P1 and the points which are closer to point P2. And you call xg the fraction of points in the Voronov cell of the first point, okay, of P1. And 1 minus xg. So maybe this is 30% and this is 70%. Okay? So you take your map and your 2 points at random and you have this variable xg. And the conjecture is that it is uniform on 0, 1. Okay? And I'm curious if anyone doing some other sort of geometry, like hyperbolic geometry or anything, has already seen a statement like this. This conjecture has been proved only for genus 0 so far by Emmanuel Guiter. And in fact, it is strongly related to this. If it was true, it would be kind of like geometric explanation of this formula by some argument that I have explained last time I was here, and then the talk is online. Okay, so just if this rings a bell, let me know.
Is it true for random trees?
For random trees, it's true. It's a result of Luigi Adario-Berri, Omer Angel, Christina Goldsmith, Eric Fusy, and myself. There seems to be no reason why something true for random trees would also be true for random maps, but it's true. It's even true for random one-phase maps of fixed genus, and it's even true if you take not only 2 points, but k points. You have a like random variable on the simplex. And the proof is a proof from the book, like a 2-line recursive trick, which doesn't really explain why it's true. So it's a total mystery. Other questions? Okay, so maybe I say a word also before going to high genus. It's also very natural to do maps of unfixed genus. So what you can also do is let n go to infinity, but do not impose anything on the genus. So for example, you could take 2 n triangles, and you just glue the sides as you want. Okay. So this is very, very different. That's the only point I want to make. This is closer to the configuration model in graph theory. So if you know what the configuration model is, you see why it is the same. And if you don't know, it's essentially this. So this is called the configuration model for people who do random graphs. And so here the big difference with before is that these gluings are essentially independent. You can do whatever you want. And you don't insist that in the end your object that you build will have a certain topological constraint, that this genus is something. So this is a very different model that you can approach with very different tools. So some people have been doing that. You can say very precise things. So I hope I'm not messing this up because I'm not very familiar with this model. But essentially what happens is that the genus will be almost maximal when you do that. If you don't constrain the genus, it will try to be very large. You will have very, very few vertices. So the number of vertices will be little O of n, and in fact much smaller than this. And so then you can say many strong things. So some people have been doing this. Many of them are in the room. And in fact, you can even generalize part of this theory to higher dimensions, and I think this was the case in Anna's talk. You can glue together tetrahedra or octahedra, and you are in kind of this world, but my point is this is kind of different from my main story. Okay, so that's the end of the review part. So you can look at maps. I want to look at maps where I fix the size that becomes very big, and I control the genus. I can look at local limits or global limits, and when the genus is 0 or fixed, essentially we understand quite well what happens. But we need some good counting technology. So for local limits, we need enumeration, and for global limits, we even need bijective counting somehow. Okay, so there's some combinatorial cost in solving these problems. Okay, so then the next idea is to try to have both n and g go to infinity. Okay, and maybe the most natural idea is to have this while with n and g being proportional. So I want to let both n and g go to infinity with g proportional to n. So g is theta times n for some theta which is not 0 and which is not 1/2. Okay, and then see what happens. Okay, so this is the hygienist regime. So g over n goes to theta. Theta is between 0 and 1/2. So maybe a first remark. So let's say I do triangulations now. Okay, so if you look at triangulations, so I have 2 n faces. So the number of edges is 3 n's because these are triangulations. And so by Euler formula, the number of vertices is n plus 2 minus 2g. So if g is theta times n, the average degree is something like 6 over 1 minus 2 theta, if I did not mess this up. But in any case, it is strictly larger than 6. Okay? And this point is inversion. But that's, you choose your notation, only for this slide. Anyway, so somehow, I mean, of course, if the genus is fixed, non-zero but fixed, the average degree is still tending to 6. But here, at the limit, your average degree is really larger than what it is in the planar case. So maybe you have some sort of curvature or some sort of hyperbolic behavior. And so this is maybe the motivation to study this regime. Maybe it will give you something truly different in the end. So let's look at it. Okay, so again, I fix theta. I consider maps of genus Gn, which is theta times n. This is a hygienist regime, and so the motivation, I said it. You expect some hyperbolicity, but in terms of kind of problem solving, it's fun because it's difficult. Okay, so compared to the last thing I said, where you have where you just glue triangles at random, you don't have independence. Okay, in the unfixed genus case, things were independent, but here I want to control the topology of the object I get at the end. So even if I want this topology to be very large, I still want it to be atypical compared to the unfixed case. So it will be very hard to control. And also in this regime, I cannot count. Okay, I said I showed you this Bender-Canfield estimate. I have an estimate for fixed g when n goes to infinity, but I don't have something like an estimate of the number of triangulations when g is large. I mean, no one knows how to get this. So it breaks. Somehow your tools are not functioning for this. So this is fun. So in fact, to be complete, I should say that there's at least one case where you can actually do this. This is called the unicellular case. It looks a little bit trivial from far away, but in fact it's not. It's already quite interesting. So in this regime, you can look at a random unicellular map. So unicellular map is a map with only one face. So in genus 0, it would be a tree, and in higher genus, it would be one of these like kernel things with branch of trees that I showed you. And you can look at this object in the high genus regime. And something like 10 years ago, a group of mathematicians, young at the time, 3 of them are in this room, and Gurabrai showed the local limit. So in this case, indeed, you have some local limit, and the local limit is it's a tree, but it is a supercritical tree, so a tree in which the balls grow exponentially fast. So you recover already some sort of hyperbolic nature. And then Gurabrai, in his PhD thesis, showed that the diameter of these objects, with high probability, meaning with probability tending to 1 when n goes to infinity, the diameter is of order log n. It's between 2 constant times log n. And I will not say more about this. So you understand both the local and the global behavior. That's my point. And in fact, the subject has been revised by Baptiste recently and co-authors with fancy hyperbolic geometric connections. And in fact, Baptiste's talk will be about this model, so I will not say more. Yeah, I will just say this, that the reason why we could do that 10 years ago is because for the local limit, we have some counting. So one-face maps are well understood. I mean, there are formulas due to Lehmann and Walsh, which were rediscovered by Harrer and Zagier in the 80s, but in combinatorics, they were known 15 years before. And the second result requires bijections, but it turns out that we have quite powerful bijections for one-face maps. So this is kind of a toy model, but the problem is so rich that even the toy model is interesting, in fact. But for the general case, if you want to do, for example, triangulations of high genus, you don't have anything like this. You cannot count these objects easily. I mean, you have these bijections that I showed, but the objects that you get in the end, they are kind of useless. So there's nothing you can do. And yeah, until recently, doing something like high genus random triangulations, this was just science fiction. Okay, this was just too hard. But I mean, since I'm talking about it, you guess that something happened. So in 2019, two young PhD students, respectively Thomas Budzinski, who was at Orsay at the time, and Baptiste Louf in Paris, did something remarkable. They proved something that was called the Benjamini-Curien conjecture, which was essentially the local limit of high genus triangulations. So what they proved is the best you can hope for in terms of local limits. So when n goes to infinity in the high genus regime, so g is theta times n, then this object T and G, the random triangulations of size n and genus G, converges to something which is called the pit of parameter lambda for the local topology. So the nature of the convergence is really local topology. So this is the same thing as my UIPT, I mean, my convergence to the uniform infinite planar triangulation that I had shown you in the first slide. And what is this pit? So it is something that was introduced, I think, by Nicolas. I hope I'm correct. It is some sort of hyperbolic analog of the UIPT. So in the UIPT, I did not explain you how you construct the UIPT, but the UIPT is some random triangulation of the plane that you can somehow construct by growing balls. And in the pit, you have an additional parameter in this growing process that makes it a little bit too fast, and then the balls are growing exponentially. So this is a one-parameter family of random triangulations of the plane, and if you choose the parameter correctly, you exactly get the local limit of high genus triangulations. So this is really a very strong result. And in fact, the proof requires very little combinatorial input. So the proof is not that they managed to count and then take the limit. The proof is that they did a lot of things, and in the end, they get the limit. Among these things, there was a little bit of counting. In fact, the proof still depends on something which is the Goulden-Jackson equation for triangulations. So people familiar with the physics literature may recognize an equation due to Nekrasov, Kazakov, Okunkov 10 years before, but I mean, this happens. Still called the Goulden-Jackson recursion. So this number, tau and g, is the number of triangulations of size n and genus G. And it is given, I don't know why they write it in this form, but by an explicit quadratic recurrence. And you could say, okay, I will prove this theorem by I will start from this recurrence formula, I will do the asymptotics when n and g are large, and then I will take ratios. But no one can do that. No one is able at least no one connected to our community is able to do to make the asymptotics of this recurrence work. So we cannot do that. This is very combinatorially mysterious. So in fact, this implies the previous one by taking n go to infinity. Yeah. So this is even more combinatorially mysterious. This is a complete mystery. This comes from this descends from the KP hierarchy, and so the fact that you have tau functions of KP hierarchy when you can map, that you have Schur functions, the representation theory of the symmetry group, and everything. So it really comes from a different place. So they use this formula, but in a weird way. Essentially, they use it to say that, okay, the right-hand side is larger than one term in the left-hand side, also, or the converse. But it's not like they can do the scaling of this formula. And then they use lots of compactness argument, measure theoretic arguments to get this result. It's not my point to describe this proof. But one thing which is even more remarkable maybe than proving this conjecture is that in fact they get counting estimates in return. So combinatorics is not good enough to provide what you need to prove this theorem, but if you prove this theorem, you get some combinatorics in return. And there are corollaries in this paper. So let me give two of them. So maybe this one is less surprising. So this is a ratio estimate. So if you count triangulation of size n-1 divided by triangulation of size n for fixed genus, it converges when n goes to infinity to some constant, this constant. So this is maybe not surprising because, I mean, if you prove the convergence, the local convergence, that I don't know, you are able to estimate precisely the probabilities that the neighborhood of the root is something very small, and if you can do that, then probably you can estimate such ratios, right? So it's not so surprising that this is a consequence of the convergence. But this, for example, is something that no one can prove from this formula. Okay, so that's very strong. And then because you have ratios of number, if you take successive ones, maybe you can say something about the full number, and indeed they can say something quite strong. So this number tau and g in the high genus regime, so g is theta n, they explode as n to the 2g times exponential constant times n. Okay. So the fact that you have n to the 2g here is not very surprising because if you take a map of genus g, in order to make it planar, you need to cut 2g cycles. And in order to go back, every cycle that you want to glue back will cost you n. And so having something of the form n to the 2g exponential big O of n is essentially obvious if you're used to these things. But the remarkable thing is that they have the exact constant here. They have a function of theta which you can plot and which is completely explicit. So this is a very difficult estimate. I mean, you cannot obtain it by any other method. So of course it looks weak because it's an estimate up to exponential little O of n, and of course exponential little O of n is huge, right? It could be exponential square root n, so it can be huge, but it's still the best one can do, and so having this exact constant here is something super strong.
The little O of n does not depend on g?
Well, g is on some, so g is proportional to n, and theta is in some compact in this interval, say. Okay. And the little O of n then doesn't depend. Does that answer the question?
In this expression, why not throw the n to the 2g into the little O of n?
Because g is theta times n.
Yeah. Okay.
So this is n log n. Other questions? So this is really it. So this is so if you put this in terms of the exponential, you have a term n log n, which is kind of obvious to guess, a term constant times n, which is very hard to guess, and this is what they did, and a reminder that nobody knows about. If you find an AOFA paper by some authors that I will not name because they are not here, who claim to have a full asymptotic expansion of this quantity, the paper is wrong. Okay. Just in case you find it. There's a consensus on this. So here's the new result. Okay, so I say, so these brilliant young people did the local limit, and then you can ask, of course, about the global properties, and we have been trying to do this for some time, and we finally succeeded. Oh yeah, by the way, there is no paper, but I mean, we have written all the proofs, okay? They are written. They have been read by at least by 3 different people, and there will be a paper soon. So we are very happy to announce that we can finally do it. So when n goes to infinity in the high genus regime, so g is theta times n, and theta is something different from 0 and 1/2, something in between. The diameter is logarithmic, so it's bounded with high probability between 2 constant times log n, and also the distance between typical points.
The lower bound is trivial, right?
Yes, almost. I will show the proof, but it is essentially trivial. The upper bound is hard. I mean, hard. It's non-trivial. So in fact, our first proof of this was based on some complicated bijections, essentially the bijections I showed you, and some enumerative estimates. But in the end, we finally understood that the bijections were not really necessary, and so in fact, the better proof, and maybe more conceptual, works by as a consequence of an isoperimetric inequality. So this is the second result. So it goes like this. So you have constants k and delta, such that for any k1, k2 that sum to 2n, so you take two numbers, k1 and k2 that sum to 2n, you just want that they are not too small. So the smallest of the two, which is k1, is at least k log n. Okay. So if k1 is less than k log n, I cannot tell you anything. But if your two numbers are larger than k log n and sum to 2n, there is no multi-curve of length L smaller than delta k1, which separates the triangulation in two components of size k1, k2. So let me say it again. So what's a multi-curve? A multi-curve is just a collection of curves on your surface. And they are not allowed to cross. So they can touch at a vertex, as here, but they cannot cross. Okay? And say that you have so this is with high probability. Okay, so this statement is true with probability tending to 1. So assume that you have found a multi-curve like here that splits your triangulation into two pieces of size k1 and k2, okay? Maybe k1 is very small. It is smaller than k log n. Then in this case, I will not tell you anything. I don't know. But if k1 is not too small, then I can say that the number of edges that you need to cut in order to make this happen has to be at least a constant. So this A delta should be a delta theta, sorry. I don't know why I wrote this. The length that you have to cut needs to be proportional to k1. Okay? So it's not possible to separate a decently big piece of your graph without cutting a number of edges which is comparable to the size of this piece. This is really an isoperimetric inequality. Okay? Makes sense? So this, if you know what the Chigger constant is, this is essentially a Chigger constant kind of statement. So what's the Chigger constant? H. What you want to do, you want to take A. So here it's the Chigger constant of the dual graph, in fact. So you want to take a set of faces of your triangulations, and you want to compare the size of the boundary with the size of the set. And you want this to be very small. So of course you're not allowed to take everything because otherwise it would just be 0. So you restrict to sets which are only half. So here half of 2n is n. And among these sets you try to make this as small as you can. Okay? So from my inequality, if A is larger than log n, this will never be very small. Okay? So the thing will be smaller. So I will mess it up, but it gives you one of the two directions. The isoperimetric gives you one of the two directions, and the other one is because, in fact, it is indeed possible to separate a piece of size log n with only constantly many edges. It's not very hard to see that in branch to our triangulation, there are many small tentacles, so some very small pieces that grow. In fact, there are linearly many of them with a linear total mass, but so among them there are some exceptional records, and the records are typically logarithmic. So you get both sides of the Chigger constant. Okay, so that's basically the results. And I want to say 2 words about the proofs, which are very, very fresh. Okay, so what's the idea behind isoperimetry? So it's essentially so it's a little bit technical, but it's essentially based on counting. So we use and we strengthen a little bit the counting estimates from this breakthrough paper by Thomas and Baptiste. So you see, let's say I look at this picture and I want to see that the thing on the right is unlikely. So I want to upper bound the count of things on the right compared to things on the left, right? So here I have a triangulation of size n and genus G, so it is something like tau ng. After I cut, I get 2 triangulations. So here the size is k1, but in order to make it a triangulation, I need maybe to triangulate the boundary. So the new size of this piece after triangulating the boundary will be something like k1 plus L, and here k2 plus L. And so I want to compare tau ng versus tau n1 g1 times tau n2 g2. Okay? And I hope to show that this is much smaller than this, so that in fact it never happens. And so you remember I have this estimate with an n to the 2g here. So if you just look at the contribution of the n to the 2g, here you have something like n to the 2g, and here you have something like n1 to the 2g1, n2 to the 2g2. So here, say that n1 and n2 are like both half of n, then this will be very big. This will be something like 4 to the 2g. This will be exponential. Okay. In fact, the only possibility for this thing not to be exponential is that n1 and n2 are both comparable to n. Both very, is that one of the two is very small. Because if they are both comparable to n, then this will just decrease exponentially with n. Okay? But on the other hand, you have a problem because you have an f of theta times n, and so this could be compensated by this term because the theta is the genus to size ratio, and the genus to size ratio could be different between these three maps. So you have many, so the proof is a little bit technical. I just want to mention that at some point, it is very important to show that this function f of theta is concave, and in passing, we thank Andrew, who's here. Thank you, Andrew, for the proof that this function is concave. Because I say it's explicit, but it is not so explicit. And then, you have a technical proof to essentially make this ID work. But the point is you need this estimate, you need some fine control of f of theta, and you need a little bit of technical mess to clean up the small pieces. Okay, then you have what Asaf saw in less than 1 second, which is a lower bound for the diameter. So for this, you need almost nothing. And so in particular, you don't need the full strength of the Budzinski-Louvre paper. So you just do first moment. So you take L, your favorite number, and you just count number of paths of length L between two random points. So you take a map, you take two random points, and you count the expectation of the number of paths of length L between these 2 points. So what you do, you slit your path open, you obtain a polygon, and you triangulate it. Okay. So here you have something with 2 points of size ng, so you have n squared to ng, and after doing this, you have only 1 point, so you have n, but you have a map which is slightly bigger, because by triangulating, you have added L polygons, L triangles. But remember, they have this very nice ratio theorem that tells you that successive ratios converge to some constant. So this ratio, you will have some constant to the L divided by n. And so if L is a very small logarithm, then this goes to 0. Okay, so this means that on average, between two random points, you have no path of size L, which means that the probability that you have a path of size L goes to 0, which means that the diameter is at least L. Okay, and maybe most interesting is why is isoperimetry related to distances at all? Well, why is it related? So let me start with a trivial remark. So in a triangulation, let's say that you have a vertex V and you look at the ball of radius R. So you look at all the faces that you can reach in distance at most R from V. I claim that, and then you look at the next one. So the ball of radius R plus 1. So this is the number of faces. I claim that the number of faces in this ball, of course it is larger than in the previous ball because they are included, but it is larger by at least 1/3 of the size of the boundary. This is kind of easy. You have this boundary, and on each edge of the boundary, you have a red triangle that will be part of this ball. So you have, but of course, maybe some of these triangles are the same because they could be interlaced together, but not more than 3 times because each triangle has only 3 edges. So you have a 1/3 here. So what this means is, if the boundary of your ball, if this quantity here in red is of the same order as the quantity in blue, say that this is at least 0.1 times that, and this on the left will be at least 1.1 times this. So this means that your ball grows exponentially. So if you are in a situation where your ball has a boundary which is large compared to the ball itself, then the next ball will be significantly larger. And then, if you combine that with isoperimetry, then you win a lot. So what you're going to do, I will not do the full proof, but just give an idea. You fix a vertex V and you start exploring a ball, and you want to prove that after something like 1,000 times log n steps, you will reach 55% of the total mass. And so what you do, you do your exploration for a time 1,000 times log n, and at every step, if your boundary is large compared to your ball, then you grow exponentially fast. So if this happens for too long, if you grow exponentially fast for more than logarithmic time, in the end you will reach whatever you want, for example, 55% of 2n, right? But if not, then this means so this is slightly wrong, but kind of correct. So if at some point your boundary is small compared to yourself, then you can apply isoperimetry. That's the point. If you have a small boundary, then the pieces that it separates have to be small. At least one of the two has to be small. So maybe you separate some pieces which are indeed small, like logarithmic, but these you don't care because just by exploring a little bit more, you will just absorb them, and so they will still be rich in finite time. And maybe you have other places with the pieces. So but they cannot be too large somehow. So you have to quantify these, but they cannot be too large, and so this means in the end that your ball has to be large. And then, of course, once you have something like this, you get the diameter, because you take 2 points, and if both of them have a ball of logarithmic radius that takes 55% of the graph, then the 2 balls have to intersect. So you get the diameter. So that's how isoperimetry comes into play in the proof of the logarithmic bound. And that's all I wanted to say. Thank you.
Thank you, Guillaume, for a terrific talk. Did I pronounce your name correctly now?
Yeah, thank you.
Okay, great. I checked it online. Any questions?
So obviously, does it extend to quadrangulations or the Boltzmann maps they were considering in a following paper?
It's not. In principle, it should, but there are a number of technical estimates. Like Andrew should prove the concavity of the function f, and I would say maybe, but I'm not sure anyone will want to do that. So in fact, we also have another proof based on bijections that we did with quadrangulations first. So we could say that maybe up to some work, we could make quadrangulations work by another technique. So I don't know. In principle, yes, but then what is the amount of work to do it? It's hard to say.
Any other questions? I have a question. If you take 2 points of such a high genus map uniformly, independently, do you expect the distance to have variance going to 0? Or is there really fluctuations?
So one thing that we show, and that I did not write, is if you take 4 points, you take at the distance between 1 and 2 and the distance between 3 and 4, these two distances, they differ by a constant, or by a random variable which is tight. Okay? So the distances are almost all the same. And then, I mean, I think we conjecture, do we? I conjecture, no, I think we conjecture that if you divide by log n, then everything converges to something deterministic. But this, I think even in the one-phase case, it was conjectured in Gourab's paper, but I don't think someone can do this. So, yeah. Okay. I think, I mean, there is I didn't say, but there are analogies with like works of Mirza-Hani for the random hyperbolic surfaces under Weil-Peterson measure, and there I think the phenomenon is similar. You have things which are logarithmic between two constants, and somewhere she conjectures that the two constants are the same, but it's hard.
Okay, so if there are no further questions, we meet again at 5:15.